So when you load the plans.avl, you should see something like that. So how many people are able to get to this step? Who are still not able to get to this point? Please raise your hand. We're not able to. Okay. I just download it. Okay. Okay. So probably very close. Okay. So I think it's now let's start talking about AVL. Okay. So this is really a command line driven interface in the sense that any place if you type question mark, you get to see what command you can execute, right? So there are two types. One type is just like load. We already used the load, right? The other type is starting with a dot. So when you use whatever starts with a dot, you actually don't type the dot. You just type, for example, opera. So the dot means it's a subdirectory of commands. So if you type opera, for example, you go into a different directory with a different set of commands you can run. Okay. So for example, inside here, you can type G. If you type G, what you see is this. Okay, so that's this airplane you just loaded. Again, like in the base directory, if you type question mark, you see the commands, and one of the commands is opera. If you go to opera, sorry, OPER. If you go to opera, you can type question mark again to see what you can run, and one of them is G. If you type G, you actually get to this.
What was the first one again?
OPER.
OPER?
Yeah.
With a point?
No point, just OPER, enter. And then type G, enter.
Do you have to have something downloaded to do that?
You have to first load the AVL file.
From online, from the modules?
Yeah, from Canvas, there is a plan.avl you download, and then like in the root directory, you type load space the full path of that AVL file. Right. Okay.
I have to type opera first. So now I should be able to load.
Okay.
Yeah, so there's no blur.
Okay, anybody else to get this work on the Mac?
Mine's downloaded 50 out of 100 megabytes.
Okay. So while you guys are downloading, maybe I'll first explain like the input of this AVL, right? Okay. So if you can open, wait. So if you can open a plan.avl using any text editor, you're gonna see it's a text file, and it's a fairly short text file, like 77 lines, with plenty of comments. So anything that starts with an exclamation mark is a comment, right? So you can delete it or change it or whatever. It has absolutely no impact to what this airplane is. Okay, so this text input, just like the AVL command line interface, is almost like a tree-based structure. So you have one section, so up to here, that defines the global properties of this airplane.
I've never played vanilla.
What? Okay. Yeah. For example, the plan vanilla is the name of this airplane, right? And this is the Mach number. So 0.0 means it's incompressible flow, and AVL is works the best for low Mach number flows. And these are almost always set to be 0. I mean, I always set it to be 0. So basically, this sets the symmetry of this analysis. And if you want 4 degrees of freedom, you basically put 0 on all of them, so no symmetry for the entire thing. So you can set arbitrary like alpha angle, beta angle, side slip, and anything like that. This line is important. It sets the reference area for us to be able to compute things like lift coefficient, drag coefficient, right? So even if you know the drag, to compute the drag coefficient, you need to divide by half of rho v squared and then divide it by some area. And that is the area you are dividing by to compute the lift or drag coefficient. In order to compute the moment coefficient, you need to further divide it by something, right? The coefficients are all non-dimensional, and the moment has force times length. So in order to compute a moment coefficient that's non-dimensional, you need to do all the non-dimensionalization. You need to divide everything you are dividing to get the force coefficients, and you need to divide further by a what? Take the moment, you divide by half rho v squared, divide by area, then you have to again divide by a length, right? So the C-ref and the B-ref, C means chord, B means span, right? Are the further things you divide to compute the moment coefficients. Now, which one do we use? We have x, y, and z moments, right? So if you look at the coordinate system, x points from the nose to the tail, z points upward, and y points in the spanwise direction. So an x moment, a moment around x, is what kind of moment? It makes the right wingtip go. It's appropriate to normalize by the span. What? And let me actually ask you, which moment does not make sense to normalize by the span, right? Which moment doesn't want the left wingtip and right wingtip to do opposite things? The y, right? The y moment actually is the one you normalize with the chord, right? Because you are not really, the y moment doesn't have opposite motions on the two wingtips. And x and z moments both are usually normalized by the span, right? Because in x and z moments, the two wingtips are doing opposite things. All right, so that's what happens with the chord reference. That's for computing the y moment, the pitching moment coefficient. And the B ref is used to compute the rolling and the yawing moment coefficients. Yes?
In like a PSET problem, are these C ref and B ref values something that we're computing, or is that something that would be given as like part of a scenario?
In the PSET, depend on what PSET, I don't know, but like usually,
I guess I'm like, wow, I'm just thinking through the process, like how would you compute that numerically?
Yeah, so I can tell you the convention, right? C-ref is usually set to the what we call the mean aerodynamic chord,
Okay.
which is the planform area of the wing divided by the span of the wing, right? So that's kind of the average chord, right? So that's usually C-ref. And B-ref, sometimes you use the full span, sometimes you use the half span. I mean,
Okay.
it depends on what is the convention.
Is that on Canvas somewhere, or is that?
You mean the convention?
Yeah.
It's not. I can write it. I can write it. Yeah. Okay. Okay. And the x and y z ref are the location around which the moments are computed. Okay. So 0, 0, 0 means it's just around the origin. But usually, if you want like proper stability analysis, right, you want these to be at the center of gravity of the airplane. Okay. So that you are computing the aerodynamic moments around the center of gravity. All right. So just for example, right, if you increase the alpha angle, the pitching moment increases. That means your airplane is longitudinally unstable, right? It further wants to increase your pitch angle. Okay. Okay. So this is the section about the airplane as a whole. So anybody had any luck with the X-Force library? Oh, it works?
Yes.
Okay, nice.
Mine also.
Nice. Okay, good. Anybody still have trouble despite the installed the X-Force? Yeah, you have a.
Yeah, I can show you the comments.
Is it doing something? No. I really can't tell. Export started.
Yeah.
It opened.
That's lucky one.
Alright, I got it to work.
The Mac is.
Oh yeah, mine's just automatically works.
Okay,
Yeah,
anybody
I
else
was
has
restarted
problems?
itself and it works.
Yeah.
Okay,
Did
so
you guys do it?
so let's continue. So this is the overall airplane, and beneath the overall airplane, there are several surfaces. So in this one, it has 3 surfaces, right? 1, 2, 3. So basically that corresponds to the main wing, the horizontal stabilizer, and the fin, right? So if you look at the surface, wing, second one is stab, and the fin, right? These are the 3 surfaces. Now, in each surface, there is a small section over here that defines the overall property of the surface, followed by an arbitrary number of sections of the surface. For example, the main wing has, I'm going to first explain this part and then explain the 2 sections, right? So this is the wing and it has just the 2 sections. In reality, you can have arbitrarily many sections. So on the wing, let me first explain the 4 parameters that sets the where the vortices are in modeling the behavior of the wing. So AVL is a computer program that computes the forces on the airplane by using what we call like a vortex method. So remember like in unified fluid, we look at the wing as if the induced flow is induced by one horseshoe vortex that goes from infinity to one wingtip to the other wingtip and back to infinity, right? In AVL, we use many vortices. So if you go back to AVL, and so this is the geometry plot, and you can turn on. So here it says true or false. For example, you can see the trailing legs are false, but if you type TR, it turns it to be true, and then it visualizes all these trailing legs. So this is the vortices we are using to model the induced flow. So each vortex goes from infinity to the wing in the geometry plot type TR. Okay, to the wing and to, not to the other wingtip, but to a small section of the wing and then go back to infinity. So over here, it has a number like 50 or 60 vortices together. Each vortex has a strength that is not known a priori, but is going to be computed as you run AVL, right? So for example, here, if you type enter to exit the geometry menu and type X to run it, so you are going to see that it computes a bunch of forces, and you can type T to see the traps plane. So that's basically, so this is Y, this is the x-axis is span, the y-axis is the distribution of lift coefficient along the span. Okay, and you also see a blue line that tells you what is the induced flow along the span. Okay, so basically these are solved by the set of vortices. So basically what AVL does is that the strength of each of these 50 or 60 vortices is an unknown. So it first tries an initial guess, and from the initial guess, it can compute the induced flow on the wing, right? From the induced flow on the wing, it knows the angle of attack of each section of the wing. And from that angle of attack, you can compute what is the lift on that section of the wing. And the lift is going to allow you to update the strength of the vortices. Now, after you update the strength of the vortices, the induced flow changes, right? So you have to recompute change the angle of attack on all the other sections. And you have to re-update the strength of the vortices, etc., etc. Basically, AVL does the iteration in a really smart way. It uses like Newton's iteration and things like that to converge to a solution. And that's the solution that enables you to compute the lift distribution and the induced flow distribution on the wing, from which you can compute the total lift, total induced drag, and things like that. All right. So this is what these numbers are controlling. The n chordwise means the chordwise number of vortices is 1. So basically there is for each section there is one vortex that is centered at the quarter chord. So that's the magenta line. If I increase, for example, this 1, 2, 3, and I'm going to reload it. load plan.avl upper g. You're gonna see, okay, this is increased so this is increased to 3, right? There are 3 magenta lines. So basically, each section has 3 vortices in this case, and there are how many? There are 16 vortices in the span-wise, right? So 16 vortices per so 4 vortices per section, and 16 vortices in this direction. So on this half of the wing, there are going to be 64 vortices in total. So 60 unknowns for this part of the wing, another 64 unknowns in this part of the wing, and there are additional unknowns on the tail, on the fin, etc. Right? So this is the collection of unknowns AVL is going to be solving. Yeah.
Does increasing the number of vortices increase the accuracy of the calculation?
Increases the accuracy, right? So for example, one of the things you can check is that when you run it, when you type X, it computes a bunch of stuff, right? And two of the things, it computes CL, the lift coefficient, coefficient of the entire airplane, and it also computes a CL far field. So this is a different way of calculating the lift coefficient, and you're going to see they are slightly different, right? And increasing the number of vortices actually makes the agreement better. So basically, it actually increases the fidelity of the flow solution. All right.
Cool.
Okay. What else? So go back to this. White duplicate is a keyword that basically tells me the wing is symmetric. So if you have a white duplicate over here, you only need to provide cross sections for half of the wing, right? As opposed to if you don't have white duplicate, if I get rid of this and save the file, if I go back to load plan.avl and plan.g, you get only half of the wing, right? As opposed to the full wing. All right, so let's get my white duplicate back. So this number is the Y location of the symmetry plane. So if you have white duplicate to be -1, you're gonna see a gap.
There's not a way to refresh it without doing all that?
At least I don't know. So here it has a symmetry plane of y equal to -1, and yeah, it's a weak plane, right? So 0.0 is proper. So this is the angle of the whole wing relative to the airplane, right? So the airplane, if is at incidence angle of 1 degree and this angle is 4, then the wing is at 5 degrees angle. Okay. So basically, this is the angle of the surface relative to the whole airplane. And now this section is the whole surface, and the cross sections are specified over here. So X, Y, Z are the location of the leading edge, right? LE means leading edge. Chord is chord, and there is another incidence angle. That's the angle of that cross section relative to the surface, right? So basically, if you think about a calculation, the incidence angle of one particular section is actually the sum of 3 numbers. 1 is the alpha of the entire airplane. 2 is the angle of the wing, and 3 is the incidence angle of the section relative to the wing. Okay, so there are summation of 3 numbers that gives you the incidence angle of the cross section, which is going to be used in the iterations to calculate the strength of the vortex. All right. Okay, so there are 2 cross sections over here, and I can talk about the control later. Basically, this is the gain of this control. So basically, how many degrees that control surface is going to be rotating. If you specify, let's say, aileron equal to 1, then this a gain of 1 means it's 1 degrees. A gain of 2 means it's going to be 2 degrees. And this is the location of the hinge. 0 means the entire surface is going to be rotating. It's like a all moving. It's weird, like all moving wing as an aileron. And this is the axis of the hinge. Or 0 means it's going to be aligned with the wing itself. And this final number is only useful when you have a white duplicate. It means if you have a white duplicate, if you have symmetric section, -1 means the other side is going to rotating opposite angles, which is proper for aileron, right? If you look at the stabilizer, this number is going to be 1 as opposed to -1. That means both sides are rotating in the same direction. All right. Okay, so this is the 2 sections. I can easily make another section. I just want to exaggerate to make it a bit weird. -4, and the y, let's make it 3, and the z, let's make it 2. Right? Okay, so I'm going to making like some kind of a Gauss wing or something like that. Wait, what am I doing?
I ask myself that every day.
I messed up something. Let me see. X, Y, Z code. XLE. Yeah, what did I specify wrong? Let's see. So this side looks fine, but Y, Z. You guys see any problem? So let's just do something that's not as dramatic and see what happens. Yeah, that looks fine. Maybe yeah, okay. So I think it might be just a visualization issue because I'm making a z and x that goes both ways. So I think it might be just a visualization problem. You can, yeah, you can basically change the view, right? Yeah, so that'll basically rotate the thing a little bit more. So basically, this is how you model airplanes, and you have other surfaces down here, right? So in the homework, I'll specify, yeah, you just do a simple wing, and do some calculations. So let me show you what calculations you can do really quickly. So go exit the geometry, and you can change the angle of attack by, right? So if you go up, you can specify angle of attack, right? So if you go upper type A, it'll ask you what you want to specify to fix the angle of attack. For example, you can just say angle of attack 4 degrees and run X. It'll recalculate all the forces, right? Alpha is 4 degrees and CL has increased to 0.8. Or you can type A and type a C. So C means CL. If I want a CL of 0.5, I can type C 0.5 and execute. It'll compute the alpha that gives me a CL of 0.5, right? And along with other forces like Cm, the moment coefficient, and you also have CD induced, right? That's the induced drag, all right? And it also computes a span efficiency E. That's basically relative to an optimal elliptical lift distribution. All right, so this is the bunch of things you can do with AVL: compute all the forces, moments, induced drag, efficiency, etc. And this file is how you model an airplane.
Which is the command to, like, if you want to change the CL, for example, oper what's the letter? Oper X?
Yeah, so first of all, you tell it I want to change angle of attack, right? And it asks you what do you want to set to get the angle to get a different angle of attack. You can directly set A, or you can set C, 0.5.
Oh.
All right.
Then how would you get it to recalculate?
X.
Got it.
You
Yeah.
get it to display like all the information like C
When you type X, it automatically does that, right? So it just just need to scroll up to see. Yeah. All right. Any more questions?
Thank you.
Yeah, sure.